Have you ever run into a problem that's so complex, it feels like the only way to solve it is to just solve a smaller version of it first? Now, that might sound like a riddle, but it's actually the heart of one of the most powerful and honestly beautiful ideas in computer science, recursion. Today, we're going to pull back the curtain on this amazing way of thinking. So here's our game plan. We'll kick things off with a classic puzzle that seems totally impossible at first. Then we'll reveal the secret weapon that cracks it wide open, recursion. After that, we'll explore how programmers use this in the real world, how to avoid the common traps, and we'll finish up by building that recursive mindset so you can tackle your own big problems. All right, let's dive right in. To really get our heads around recursion, we need a problem that shows off just how powerful it is. And you know what? There's no better example out there than the classic puzzle known as the Towers of Hanoi. Okay, picture this. You've got 3 rods. On that first rod, there's a stack of discs, all different sizes. The goal? Super simple. Just move that whole stack over to the last rod. Sounds easy, right? Well, not so fast, because there are some very strict rules you have to play by. Okay, rule 1, you can only move a single disc at a time. Rule 2, it has to be the top disc on a stack. And the big one, rule 3, you can never, ever put a larger disc on top of a smaller one. Now, with just, 3 discs, you can probably figure it out. But once you start adding more discs, the number of moves you need to make just explodes. So, trying to solve this by just guessing the next move, that's a dead end. The way forward is to change how you think about the problem entirely. And the elegant key that unlocks this whole puzzle is a concept called recursion. So what is recursion really? At its core, it's actually pretty simple. It's just the idea of solving a big problem by solving a smaller version of the exact same problem. You take a big task and you break it down into identical but bite-sized subtasks. This might feel a little weird at first, kind of like you're just going in circles without making any progress. But with recursion, every one of those circles is actually a step forward. You're simplifying the problem each time, getting one step closer to the final solution. So how does this abstract idea actually help us move a stack of disks? Well, it's all about noticing that the puzzle is self-similar. See, the steps to move a stack of 5 disks are pretty much the same as moving a stack of 4 disks, just with one extra little step in the middle. Okay, here's the magic. To move a whole stack of n disks, you just follow these 3 steps. 1, you pretend the biggest disk isn't there and solve a smaller problem, moving the top n-1 disks to the middle helper rod. 2, you make one super easy move, the giant disk at the bottom goes to its final destination. And 3, you just solve that same smaller problem again, moving the n-1 disks from the helper rod right on top of the big one. That's it. But wait a minute, if the function keeps calling itself to solve a smaller problem, how does it ever stop? This is maybe the most important piece of the whole puzzle, the base case. It's the simplest possible version of the problem that doesn't need recursion. For us, if someone asks you to move a stack of just 1 disk, well, you just move it. That's the kill switch that stops the process from going on forever. Now, there is a catch to this really elegant logic. It has a cost. The time it takes grows exponentially. That's what O of 2 to the power of n means. For every single disk you add, the number of moves basically doubles. The space cost, O of n, is a little better. It means the memory needed grows in a straight, predictable line as you add disks. The computer has to remember every step it's in the middle of, and that adds up. So this is a huge takeaway. Just because a solution is elegant doesn't mean it's the most efficient. So that brings up a really practical question. The Towers of Hanoi is a great demonstration for sure, but when would you actually use recursion in real-world code? Where does it really shine? Okay, so recursion is an absolute superstar for problems that are naturally nested or branch-like. Think about your computer's file system. A folder can have files and more folders, which have their own files and folders. See, it's a perfect fit. But for simple, straight-line tasks like counting from 1 to 100, a basic loop is usually way clearer, way easier to read, and it doesn't eat up as much memory. And here's the real advice, the bottom line. Recursion is a tool in your toolbox. It is not a golden hammer. You don't have to force it on every single problem. The real skill is knowing when its elegance is the perfect solution and when a simple, straightforward loop is just the better way to go. And, like any power tool, if you're not careful, things can go wrong. There are a few classic mistakes that pretty much everyone makes when they first start getting into recursion. The biggest trap by far is forgetting that base case, that stop condition.
Without it, the function just calls itself forever and ever until the program runs out of memory and crashes. That's what we call a stack overflow. Another common slip-up is when your recursive call doesn't actually make the problem any smaller, so you just get stuck in a loop going nowhere.
So what's the best way to avoid these headaches? It's actually super simple. Just start small. Don't try to test your recursive function with a massive number. Test it with the absolute easiest cases you can think of, like n equals 1, then n equals 2, then n equals 3. If it doesn't work for the simple stuff, it's definitely not going to work for the complicated stuff. Okay, let's bring this all home. Thinking recursively is more than just a programming technique. It's really a whole new way of looking at problems, both in and out of the world of code. So here's what you really need to remember. Every recursive solution has two essential parts: a base case that says stop, and a recursive step that makes the problem smaller. It's the perfect tool for problems that look like they're built out of smaller versions of themselves, but always keep an eye on memory usage. And the real test of whether you get it, if you can explain step by step what the computer is keeping track of, that's the call stack, then you've truly mastered it. And that brings us right back to where we started. Recursion shows us that for some of the biggest, scariest problems out there, the solution isn't some complex formula. It's hidden inside the solution to the tiniest version of the problem itself. It's this beautiful, logical loop that, once you really see it, can change how you solve things forever.